Good. All right, thank you. Well, thank you for having me. Tonight, I'd like to take us on a journey to the center of the virtual machine. So I'd like to start with this quote. It says, if you talk to a man in a language he understands, that goes to his head. If you talk to him in his own language, that goes to his heart. So there's at least two problems with this quote. One, obviously the language can be made more inclusive. But two, there's actually no evidence that Nelson Mandela ever said this, which I discovered when I went looking for a source. But I think there is something really interesting in this idea. Maybe that's why it's been repeated so many times. It says not only is language important, but the choice of which language we choose to use. I also like this quote. I think anyone who's tried to learn a second language can identify with her. And finally, one more. This might seem like an anachronism in a few years, but right now I think it is still valid. It says, programs must be written for people to read and only incidentally for machines to execute. And I think this is quite true. I think we really are trying to communicate with other human beings. And much like natural languages, computer languages are also social constructions and the results of the choices that people make. So a little bit about me. I'm part of the SpiderMonkey team at Mozilla. I'm a delegate to TC39, which is the committee responsible for the JavaScript programming language standard. And my free time, I enjoy reading, learning languages, mostly Spanish, and lately I've been attempting to learn how to knit. So what then is a spider monkey? It's a member of the genus Ateles. It's considered the most intelligent New World monkey, and they don't have much in the way of thumbs, but they make up for it with their long limbs and tails. So what then is SpiderMonkey? That's the JavaScript engine that's used in the Firefox browser. The engine is part of the browser that's responsible for executing JavaScript code. Consists of parsers, interpreters, just-in-time compilers, garbage collector, and a library of useful functions, built-ins. I'll be going into more detail each of these tonight. But first, I'd like to talk a little bit about TC39. This might not be the most systems-y topic, but I hope people will have a little bit of interest in how language standardization works. So what is it? Well, it's Technical Committee 39 of ECMA International. It's responsible for ECMAScript, standard for JavaScript. We can't call it JavaScript because Oracle still owns a trademark. It's formed by a group of companies, nonprofits, and universities that are all interested in the future of JavaScript. So why are standards important? Well, it's an agreement on the functionality of a system, and this is what allows independent implementations to exist while avoiding problems with intellectual property lawsuits and that kind of stuff. It's the only legal way that competitors like Google, Apple, and Mozilla can collaborate in the future of JavaScript. So how does this committee work? We meet 6 times a year. There's presentations with proposals to change the language or improve the language, and we discuss these and sometimes argue about them. But in the end, the decisions are made by consensus. And this means that each delegate has the power to block the advancement of a proposal. So there's good parts and bad parts of that. The good part, this means that every organization, no matter how small, has a voice in the design of the language. The risk is that we end up with a language where every individual part is kind of nice, but all of the parts don't really make sense as a whole. So at TC39, we have 5.7 stages that a proposal goes through to become part of the language. First stage, stage 0, is basically any idea to improve JavaScript. And so what's going to happen is that the people who are proposing the change, called the champions, they will create a repo, they'll have a README in it, and hopefully it will include a clear statement of the problem they're trying to solve, and possibly some ideas for solutions as well, but the really important part here is the problem statement. If the committee agrees that this problem statement makes sense and it's worth spending time on it, then the proposal can advance to stage 1. At this point, the champions will be working through the possible solutions and developing a sketch of the specification text. If there's agreement that this change should be part of the language, then it could advance to stage 2. And at this point, chosen a solution, there's agreement that will be part of the language, and the champions can go through and write the full specification text for the change that they want to make. Once that is complete and there's general agreement that this does in fact make sense, then it can advance to stage 2.7. This is relatively new, hence the 0.7. And this part is about creating tests. We have a library called test262, which is full of tests for the standard. We debated 0.7 for 3 or 4 hours and narrowly missed calling it stage 2.62, which is unfortunate because the testing library is called test262. But once we have enough tests, we can move on to implementation and engines. So at this point, the specification is considered stable, and begin implementation. Advancement at this point requires 2 independent implementations as well as significant experience with the change on the web. So this basically means that 2 of SpiderMonkey JavaScript core and V8 have implemented the change and shipped it. And once that happens, we hit the happy stage, and that's when the proposal becomes part of the specification. So that is the happy stage. So not every proposal will advance. And that's because sometimes there's a disconnect between how champions view their proposal and how other people might view their proposal in the committee. So our team, what do we think about when we think about proposals? We have 3 priorities. One of the most important, is this actually good for the web? Second, is this something that there's evidence that JavaScript developers actually want? And third, is this something that we can actually implement efficiently in the engine? And these sometimes conflict with each other. This is the prioritization. But for instance, if we have something that's not efficiently implementable, even if JavaScript developers want it, we would say it's not really good for the web because people have performance expectations for JavaScript that runs on the web. And with that, I'd like to move on to the next part of my talk, which is about the architecture of SpiderMonkey. So here, probably a little bit small, but it doesn't matter. So this is my first attempt at drawing an architecture diagram for SpiderMonkey. But actually, hopefully that's visible as well. I actually like this one quite a bit more. I found it in an old Italian poem. But anyways, starting here, we have our JavaScript code that comes from the user. Though we might like to think that it's living in a holy city, it has more often lost the path in the dark woods. And at that point, I can start talking about the front end of the engine. And so what is the front end? Basically, this part is what's taking JavaScript source that's provided by the host environment. So that can be the browser, that could be Node if you're using Node, and transforms it into a format that's usable by the rest of the engine. So just like Cal, the engine has its entrance, abandoned hope, yeah, you enter here, and that's a tokenizer. So what's a token? That's an indivisible part in the input of an interpreter. And the tokenizer is just going to divide that input text into a list of tokens. So you can see here, like a keyword like let is actually a single token, even though it consists of multiple characters. But this is a very, very simple part. Once that's done, then we can move on to the parser. So what the parser does is it's using the language grammar for JavaScript and taking this list of input tokens and using it to build an abstract syntax tree. So in SpiderMonkey, we actually have 4 parsers. We have a syntax parser that runs quickly, but it's basically checking for syntax errors and other early errors in the specification. And then we have what's called the full parser. So that's slower because it's going to do the work to build the actual abstract syntax tree. And as it turns out, we have 2 versions because of text encoding. So we have UTF-8 and UTF-16. That's a design decision that we've made. My understanding is that V8 just transcodes everything to UTF-16. Okay, and the last part of the front end is the process of bytecode generation. So what's a bytecode? Bytecode is just an instruction for a virtual machine, and virtual machine is just an abstract definition of a computer. I realize in these days of containers, we usually think of virtual machines as emulations of actual CPUs, but in SpiderMonkey case and other JavaScript engines, we're defining something that's much closer to JavaScript language than an actual CPU. So our process of bytecode generation, we'll have this input function, and here you can take a look at the bytecode that's being generated for it. You might be able to notice that we use a stack-based virtual machine, so we're pushing elements onto the stack and then popping them off to do operations on them. And over on the side, I have a diagram. So our source code comes in, it runs through the tokenizer and the parser, and that's runs through. Then we walk through the abstract syntax tree that's being generated to create bytecode, and then that's ingested by the interpreter. Okay, and with that, I can start talking about interpreters. So what's an interpreter? It's just a program that runs the instructions for another program. So there's 2 common ways of implementing something like this. One is just to walk the abstract syntax tree directly and interpret the operations there. This is apparently how earlier versions of Ruby are implemented. So it's going to be simple to implement, but it's usually not very fast. And the approach that we take and the other engines take, which is by implementing a virtual machine. And in this case, what we're doing is we're just running in a giant loop. There's basically a case or computer go-to for each bytecode that we implement one by one, and this is usually faster. So we have 2 interpreters in the engine. The simplest one is what we call a C++ interpreter, and this is just, it's an implementation in C++ of each bytecode that we support in the virtual machine. And so here, C multiply, just popping 2 values off the stack, multiply them together, and pushing the result back onto the stack. We also have what's called the baseline interpreter. So this is similar to the C++ interpreter, but what it's doing is it's also collecting type information and other metadata as it's running. So if we look at this function again, say the parameter x is likely a number, probably an integer, but is there any way that we can make use of this information? And so here, I'd like to make a little digression and talk about types for a bit. So this is Bertrand Russell. Beginning of the last century, he was involved in a program to axiomatize mathematics, which means he wanted to show that everything in arithmetic and mathematics could be provable by simple logic. And if he looks a little bit concerned, it's because he has this problem. And this problem is what we call today Russell's paradox. In words, it says, consider the set of all sets that aren't included in themselves. And it's only included in itself if it's not included in itself. And that's a serious problem for him because it's a contradiction, and anything is provable from a contradiction. But he had a great idea on how to solve this problem, which was to invent types. And essentially, what he did is if we give sets a different type from other elements, then stop people from doing silly things with them, which is more or less what we use types for today. But then, what exactly is a type? It's a set of values with a rule for determining membership, has a set of allowed operations, and possibly an underlying machine representation. So to give an example of this, we can look at JavaScript numbers. So we have a rule for determining membership. We take all valid IEEE 754 double precision numbers, except we only have one single not a number value instead of the over 9 quadrillion possible not a number values that are permitted by the standard. There's a reason for that, and that's because we can pack a 32-bit pointer inside a NAND value inside the engine. And we have our set of allowed operations with multiplication, division, addition, subtraction, etc., and an underlying machine representation, which is given to us by IEEE 754. You can notice the sign bit there. That's why JavaScript has the lovely feature of plus and -0. Some other concepts that are important. So type checking, determining whether programs follow the rules for using their types or not. This can be done at runtime, which is dynamic typing. It can be done at compile time, which is static typing. And we also have type inference, which is determining the type of a variable depending on how it's being used. So here we can guess x is a string. And then a couple more concepts. So soundness and completeness. I'm going to make sure I read this so I don't confuse them. A type system is sound if no program with type errors will type check successfully. And a type system is complete if every valid program can be type checked successfully. And so, as an aside, Kirk Gödel showed in 1930 that any sufficiently complicated proof system is either unsound or incomplete, which ruined Bertrand Russell's project. So it's probably impossible to talk about types in JavaScript without mentioning TypeScript. So here is my confession time. I'm a C++ developer. Don't cry for me, I'm already dead. But I'm also far from an expert on TypeScript, so I'll do my best here. So what is TypeScript? Basically, it was designed to allow gradual addition of static typing to JavaScript, allows for type annotations, does static type checking where it can. We use type inference where it's possible, and transpiles back down to vanilla JavaScript. So you may have heard that TypeScript is unsound, and that's actually really easy to find an example of. So in this case, we have an array of numbers, and we have an x that's a number, but if at runtime we access something off the bounds of that array, it's actually going to be undefined, but as far as TypeScript is concerned, it's a number. So is this actually a problem? Not really, because the design goal of TypeScript was to be able to reuse as much existing JavaScript code as possible. So it was much more important for designers to be complete rather than sound. Anyone have an example of a language that's sound but incomplete? Okay, I do. Rust barrel checker. So the barrel checker in Rust is sound but not complete. So that means if code passes the checker, we know that it's safe. But it also means that occasionally perfectly fine programs will be rejected. So this happens a lot when you're a beginner in Rust, or at least it did in my case, where you kind of have to train yourself to think like the barrel checker. And there's also apparently still an open issue in the barrel checker, so it's actually neither sound nor complete. Okay, one last concept, and I'm going to jump back to the architecture stuff. So dynamic dispatch is when we choose which code to execute based upon the type of the argument. So here we have our JavaScript function again. If we call it with numbers, obviously we have to handle arguments that are numbers. But since JavaScript is a flexible language, we can also call it with strings and be prepared to handle strings. And since JavaScript is a very flexible language, we can also call it with Booleans and need to be prepared to handle Boolean arguments as well. So how do we make that fast? And the answer that we have is called inline caches. And this is nowhere near a new idea. It goes back to the implementation of Smalltalk. This paper that I have on the side here is from 1983. It's probably 5 or 6 when it was written. But generally, yeah, the idea is what we're going to do is cache the results of previous dynamic dispatches at the call site. And what we can do is kind of add some guards for the types. So for instance, if we know it's an int32, we have some guards. We can rapidly check that it's an int32, and then we can run through a fast path for that. And if it fails those guards, then we just fall back to the slow general purpose path where we deal with Booleans and strings and whatever else JavaScript developers want to throw at us. So in SpiderMonkey speak, we call this a stub. So this is just a chunk of native code that's been specialized for the operation in the type. But this is enough to give us about a 2x speed up over the C++ interpreter. And we do this in what we call a baseline interpreter. And so here, in this case, we have these 2 stubs. So we have int32 mul. That's just going to check that the types on the input types are int32s. If they are, it's going to do a fast path. And if not, we'll fall back. So with that, I can start to talk about just-in-time compilation. So what else can we do to make this whole process faster? And the answer is just-in-time compilation. So if we see the same source code often enough, what we'll do is we'll compile it to native code. And this is going to make use of type information that we've gathered from the inline caches. So in SpiderMonkey, we have 2 levels of JIT. We have what's called a baseline compiler, which is about the simplest possible thing you can call a compiler with a straight face. It's very quick, but it's not really doing any kind of optimization. And then we have Ion, which is our optimizing compiler. So it's going to be a lot slower, but generate better code. Other engines, for instance, V8 actually has 3 levels of JIT, so they're finding a middle tier in here that we don't have present. So why do we compile code at runtime? Ahead-of-time compilers for JavaScript definitely exist, but in our case, since we're focused on browsers, we know on the web that most JavaScript code is only executed once, or possibly never, which is why tree shaking exists. And we also know that compiling and optimizing code takes time, which means that we face a trade-off. And that trade-off is if the time to compile plus the faster execution time for this compiled code is greater than the time that would have taken to interpret it, then there's no point in compiling the code because for as far as the person looking at that website is concerned, it's going to be slower overall. Okay, so first compiler, baseline compiler. So we already have the baseline interpreter and we have the inline cache. So what more can we do here? And the answer is we generate native code for the other operations. So we'll stitch together a little bit of native code for pushing 8-bit integers onto the stack, another one for pulling an argument in and pushing it on the stack, etc. And then what we can do is take each one of these little chunks of native code and stitch them all together. And that will give us a chunk of native code that we can then use. And we're still using the exact same inline caches as before. And so this is what the baseline compiler is doing. And baseline compiled code ends up being roughly twice as fast as the baseline interpreter. But the nice thing about this design is that a lot of code is shared between the two. So we're still using the exact same inline caches between the two. But the other kind of nice thing is we can actually generate the baseline interpreter using these little chunks of native code that we use to make the JIT compiled functions here as well. Okay, and with that, the last part of the JIT is called Ion. So I'll be a little bit more hand-wavy here since I haven't worked on this part of the engine, but I'll do my best. So we have 2 inputs. So we have the bytecode that we generated way back when we were walking the abstract syntax tree, and we have what's called cache IR. So this is the representation that we're using internally for the inline caches. And we take both of those and input to what we call warp builder. And that's going to produce an intermediate representation that we call mirror. So my colleagues have written a very nice paper about this. One thing that I found particularly interesting is that before we had the inline caches and cache IR, we used type inference across the engine. And that actually generated better code than what we're doing now with warp builder. But the problem was all this type information was being collected in disparate parts of the engine. So we ended up with a very brittle system where someone would forget to update some part of the engine that wasn't closely connected with something else, and we'd infer the wrong type, and inferring the wrong type is a serious problem in terms of security for us. But anyways, moving on, so we have mirror, and that's what we run through the optimizer, so that's going to do things like classic compilers class kind of stuff, like dead code elimination, folding constants, that kind of thing. And then we generate a lower level intermediate representation that's called leer. So at this point, we need to worry about register allocations. So This is one of the most difficult problems that compiler developers face. If you think about 32-bit x86, you know there's only a handful of registers, but even on a platform like ARM that is more generous with registers, it still ends up being a very difficult optimization problem. And we know that our register allocator is suboptimal. It's just that every attempt to make it better has actually made performance worse somewhere else. So we are stuck with it for the time being. But once we have registers allocated, then we can do this actual process of code generation and generate our native code. This native code will end up being about 50 times faster than running things through the C++ interpreter. But that's the happy path, and we don't always hit the happy path. So what happens if we see an unexpected type? Well, this is what we call a bailout. And what we need to do is reconstruct the state in the baseline interpreter as though the JIT never existed at all. So we do this work, we bail it back to the baseline interpreter, and we run code just as if we'd never optimized anything. And the problem is if this happens often enough, we're going to end up throwing away our JIT compiled code because we're not using it enough to justify the amount of memory that it takes. So this is a situation that we'd like to avoid if possible. So looping back to TypeScript just quickly, does using TypeScript actually help us out? And the answer is, it certainly doesn't hurt, because anything that makes the input more predictable is going to end up with better use of inline caches and make it more likely to JIT compile code. But the problem that we face is that TypeScript types don't always match the engine types. So we know TypeScript has number, but internally SpiderMonkey uses int32 and double. And we also saw this in the soundness example earlier. So TypeScript type checks something as a number, but it's actually going to end up being undefined at runtime. So in the end, there's no guarantee that a TypeScript type is going to match what the engine actually sees, which means we have to prepare to do the exact same work, regardless of whether people are using TypeScript or not. Okay, well that covers the JITs. This handsome fellow off to the side is our garbage collector. So the garbage collector is actually one of the most important parts of the system, at least as far as performance goes. And what it's doing is managing the allocation and deallocation of memory automatically. And it does this by maintaining an object graph. So the roots of this graph are the objects that we know are in use. So in my diagram here, the little circle in fuchsia is a root. And then what we do is we have a mark and sweep algorithm. So anything that's connected to that root, so anything that's also marked in fuchsia, we know is still in use. And any unmarked objects can then safely be freed. And that still works even if there's cycles between these unused objects. In SpiderMonkey, we use generational garbage collection. So what that means is we have our cute little newly allocated object here, and that goes to live in what we call the nursery, along with all the other newly allocated objects. But it's a sad fact of life that newly allocated objects usually don't last very long in JavaScript programs. So what we end up doing is what's called a minor garbage collection. And what we'll do is we run the mark and sweep algorithm over everything that's in the nursery. We'll collect anything that's no longer in use, and anything that's still in use, we will move to what we call the tenured heap. And so the fundamental assumption here is that if something lives long enough to make it through a minor garbage collection, then it's going to be a long-lived object, and we don't need to worry about collecting it for a while. But all good things must come to an end, and periodically we also run what's called a major garbage collection. And this is more or less doing the exact same thing, except anything that is not collected will end up back in the tenured heap. And we can also use this as an opportunity to do things like compacting memory. That's not the entire story, at least in a web browser, because we also have to worry about DOM objects, which are typically, or I shouldn't say typically, are implemented in C++. And so we can get in a situation where they're holding a reference to a JavaScript callback, and that JavaScript callback can then be holding a reference to that DOM object or another DOM object. And these cycles are invisible to our garbage collector. And so inside Firefox, the DOM objects are being ref counted. So as people reference them, we increment a counter. If it goes to 0, we free it. And so they're also being allocated from a separate heap. And the end result of this overall system is that we need very careful cooperation between the DOM cycle collector and our garbage collector. This is also another area where we're sort of facing a unique problem. So V8 has solved this problem. They've created a library that unifies cycle collection and garbage collection. That's something we'd love to be able to do as well, but as you can imagine, that's a very large project. Okay, and then the last little bit I'd like to talk about are the built-ins. So JavaScript doesn't exactly have a standard library. We have a global object, and we have some other well-known objects that hang off of it, and they more or less provide the equivalent of what would be a standard library in another language. So things like math and string, internationalization stuff, map, set. And for us, we're implementing this in a mix of self-hosted JavaScript and C++, which means we're using JavaScript in the implementation of JavaScript where we can, and then we're doing C++ where it's necessary. So this is sometimes for performance reasons, and can also sometimes just be to use third-party libraries. So for instance, internationalization, we use ICU, which gets international components for Unicode, and that's the same library that's used by Apple and Google as well. And self-hosted JavaScript is a subset of the total language, so we're restricting it carefully to try to avoid security problems. So an example of a problem we had in the past was prototype pollution. So someone messes with a prototype of a built-in object, and then we use it in self-hosted code, and we end up running user code in places where we don't expect it, and that's a source of security problems. So I took an example. Hopefully this is the simplest example of a built-in function. I tried my best. I think everyone knows what set union is. Just in case, I took some text shamelessly from MDN. But yes, we have two sets as arguments, and we're creating a third set that's a union of the two sets that are being passed in. So what does this look like in the specification? So it's just a list of steps, and I'll show you quickly what the implementation looks like in self-hosted JavaScript. So you can, not the easiest thing to read, but we end up with a very close correspondence between the specification text and the JavaScript code that we have to implement this. And so I will go through that briefly, kind of step by step. So in this case, we're doing exactly what the specification says to do. This next step is a little bit different. So it says require internal slot. An internal slot is this we call like fiction inside the specification. So it's something that exists in the specification that isn't necessarily implemented inside engines. So in this case, the set data slot is a way of identifying set objects. Inside the engine, we have other ways of doing that check. So that's why this thing looks a little bit different. So step 3, get set record. So what's this get set record thing? Well, it's another thing that's in the specification. This is what's called an abstract operation. So this, again, is something that exists in the spec but isn't actually exposed to user JavaScript. And in this case, we've just implemented this in self-hosted JavaScript code as well, just in the function that's not exposed to the user. So next up, we need to retrieve the iterator and the iterator.next method. Step after that, here we're doing things a little bit differently again. So the spec says to make a copy of this set data slot and then create an object using it. In our case, we're just going to create a set copy of the original object, and that makes it an object right away. So this is an example where we can not only not do what the specification says, but we can change the order of steps. And we can get away with that as long as there's no observable difference to end-user JavaScript. So next up, we're going to iterate over the objects in the other set. And once again, it's fairly close to the specification, but there's a few things to look at. So we have this allow content iter with next thing. This is because we very carefully control iteration in our self-hosted JavaScript, because the iteration protocol can allow you to run user-defined JavaScript, and running user-defined JavaScript is bad for us inside our self-hosted code. And then the other part is the standard set add. So this is where we jump into C++. We can't just rely upon the prototype method on set because someone might have changed it on us. So we have to be very careful to call the one that we've defined. And so I won't go too far into the C++ code. It jumps through a few steps, and we end up in the set object and this add method. And then here we're using a hash table. And we're using C++ because our hash table is written in C++ for performance reasons, and the easiest way to have access to it is through C++. I meant to say earlier, and I forgot, sometimes it's actually better for performance to keep stuff in JavaScript because we pay a cost every time we have to cross the boundary into C++. And we can also JIT compile or self-hosted JavaScript. So it's not always better for performance to do C++. Okay, last step for set union is return the result. So last part of my presentation, which is why do we bother? So I was interviewing interns a couple months ago, and one of them straight up asked me, why do we bother with SpiderMonkey? And I think that's a perfectly valid question. So why do we have our own JavaScript engine? Why not just use V8? Backing up a little bit further, why do we have our own rendering engine? Why do we have Gecko? Why don't we just use Blink or WebKit? And to show that it's a valid question, there are some cases where we just don't bother. So it's been ages since we maintained our own regular expression engine. Right now we use IRRegex, which is the engine that V8 uses. In the past we used the engine that was part of JavaScript core. So it is a perfectly valid question. And the answer comes back to Mozilla's mission. So we're a nonprofit organization. We have a manifesto that describes our mission. Number of things that are in there. The one that's always spoken to the most to me is this one, which is the internet is a global public resource that must remain open and accessible. So, question time again. How many JavaScript users are there in the world? I will answer my own question. They say that JavaScript is the most popular programming language in the world, and there might be 15 million developers. But I'd argue that that's not actually the number of users. So I think anyone who ends up using the internet is actually affected by JavaScript, which means we actually have more like 5 billion users. I realize some people still disable scripting, but I think that's kind of rounding noise when you're talking about billions of people. So I'd argue JavaScript is also a global public resource. It's important to everyone who uses the internet, not just JavaScript developers, not just people who happen to speak English or live in North America or Europe, and certainly not just a handful of large tech companies. But from my experience at TC39, I'd say that less than 50 people are making the decisions about the future of the language. So why do we bother? The answer is building SpiderMonkey. It's what gives us a seat at TC39, and that in turn is what gives us influence over the future of JavaScript. And what we try to do, and obviously we're not always successful, but we try to use this influence to ensure that JavaScript develops in a way that's good for the web. So interested in learning more about TC39. So there's a TC39 website. The GitHub repo is possibly more interesting because it has sub-repos for every proposal that's under consideration. Everyone in the public is welcome to open issues, ask questions, and contribute that way. Adding tests through test262 is always welcome as well, although possibly not the most fun way of contributing. In terms of working more directly with TC39, obviously you can start working for a member company and become a delegate. A number of people have also become invited experts, and also the OpenJS Foundation is a member, so that is another route to becoming a delegate if you're interested in standardization. If you'd like to learn more about interpreters, I always recommend this book by Robert Nystrom, Crafting Interpreters. Covers everything I talked about tonight in more detail except just-in-time compilation. And about SpiderMonkey itself, we have an occasionally updated website and a matrix channel. If you're interested in an open source project, I do have a handful of small projects that are open. And I'd like to leave with one last quote. So this says, more or less, dream. It turns out, if you don't rush to change the world, it's the world that ends up changing you. And with that, thank you. Any questions? Yes.
So you talk about optimization with types, right? Is that, and you mostly use primitive types, built-in types like integers or strings. What about objects?
So there is. Of course. So the question was about optimization and whether it was mostly using primitive types or if we also optimize using objects. And the answer is yes. So certainly for built-in objects, we have a number of places where we have fast paths where because obviously the problem with JavaScript objects is that user JavaScript code can always change the prototypes on us, right? But we have what we call fuses, which are a way of detecting whether someone's modified with the object or not. And if it hasn't been modified, then we do have fast paths in the code that just can assume the type of the object as well. So the area I'm most familiar with this is in regular expression code, where we can jump through. There's a number of fast paths, for instance, like searching with groups and things like that. And then for user objects, I'm less familiar with that part of the engine. I know we do keep track of what's called the shape of the object, which allows us to rapidly check if it's has the same methods as another object. But I'm not quite sure exactly how that would be used in optimization.
Nice.
Yes?
So the specification for that union method, even though the concept is very simple, looks very complex, and also it branches to some abstract method that you showed. Why is it so? Is it to guard against, JavaScript programmers changing the set in runtime?
So let's see. So the question was, I'm going to go back to the specification so we can look at it. So the question was, why is the specification, hopefully I'm paraphrasing right, why is the specification so complicated, and does this help us with problems with user code at runtime? And so that is a very valid question. I agree this is quite complicated, and it takes a while to get used to reading specification text. I don't think the problem here, and we do sometimes specify things to avoid problems at runtime. In this case, I think the goal was more to just be very precise about the behavior. Is that okay? You have a follow-on, or?
Yeah.
Yeah.
I do find that the JavaScript specs to be very almost like pseudocode. If you read some other language spec, it's like, oh, this is math. It's very I feel like it's a community difference.
Yeah, that's interesting, because the only other one I've looked at is WASM, and I'm sorry, I should repeat the comment. So the comment was that JavaScript spec code looks a lot like pseudocode, and that other language standards aren't as easy to read. And my response would be that the only other one I've looked at is WASM, and WASM's using a mathematical kind of formalism as opposed to JavaScript. So I do have limited experience looking at other language standards. But like I was trying to say, it does map very nicely to self-hosted JavaScript. And often even in our C++ code, we're able to follow the steps of the specification quite closely. Thomas?
I was wondering if there are times where you actually have multiple JIT paths that are hot paths at the same time. So you described that you could go down a JIT path and then have to bail out. If I were to think of a scenario where maybe somebody's doing the combination of arrays and somebody was also doing the addition of two numbers, and those were both frequently used. I don't know, psychopathic person writing this code, but that happens. Are there scenarios in which you can have multiple hot paths?
Okay, so the question is whether we can have multiple hot paths that would lead to JIT compiled code. So we're JIT compiling at the function level. Mm-hmm. So we'd compile the whole function. And there's a very nice diagram which I probably should have included in my slides, which shows how the escalation of things works between C++ interpreter. So if we hit there's a counter basically, and if we see the same code something like 50 times, that's when we move to the baseline interpreter. And then I unfortunately cannot remember the numbers for the other stages, but generally, yeah, it's goes up to maybe 1,000 times is when we'd start ion compiling something. So, but then your question about whether bailing out, my recollection, and again, this isn't the part of the engine I work on most directly, is that we bail out right back to the baseline interpreter. Mm-hmm. So I think once we've moved from baseline compiled code to ion compiled code, we would toss out that baseline compiled code just to be able to free its memory, so we're not using a bunch of code to store compiled code, a bunch of memory to store compiled code.
Thank you.
Yeah. Yes.
So I have two questions. One is very related to something that you just said, which is in Ruby, why did we saw issues with the JIT compiled code becoming too much of a memory hog itself, and so there was a problem of how do we garbage collect the JIT code? Is that a big issue in SpiderMonkey, and is that different from V8?
That's a very good. It's a very good question. I wish I knew more about the answer. I know we do garbage collect JIT code, and it's my example in the slides was because we've hit a bailout and we no longer think it's going to be hit often enough to justify its use. I would expect that we would also look at stuff that hasn't run for a while and start garbage collecting that as well. But I don't work on a garbage collector, so I'm not entirely sure how that part's set up. And you had a second?
Yes. You mentioned that V8 does normalization of every string to UTF-16. Why is that? Seems wasteful.
So it's the source code. There's a source code. Yes, that's my understanding. I can't remember which direction it goes, but it's either everything UTF-16 to UTF-8 or the other way around. Yeah, I'm not quite sure. It was something that we discovered recently, that we're weird and that we have separate paths for UTF-8 and UTF-16, and they're doing it differently, and we haven't had a chance to investigate to see if we'd see a performance improvement if we made that change. I would assume that they investigated both options and did it because they saw a performance improvement, but yeah, to me it does seem wasteful as well.
Thank you.
Yes?
So, presumably this doesn't exist, but are you aware of any efforts or like anything where you can see that certain functions got compiled into JIT? Like in like a debugger view, for example?
Oh.
Because like that's what I'm trying to do with the software I'm running, is to try to JIT, like force the JavaScript to JIT basically most of the program to make it fast. And like we can't tell for sure, we're just right?
Yeah, so the question is whether it's, if there's a way of telling, like through developer tools or something, if code ends up being JIT compiled or not. And so my answer is I don't know, but we do try to kind of hide this from people, right? So I sort of suspect that there's not, but yeah.
Because you said it's on function level, right? So then like theoretically maybe I would be able to extract that information out.
And no, it's, I mean, the other thing that, and this has come up as well at TC39 from Google, I believe, where they had some ideas around adding like compiler hints or something, saying please just JIT compile this function, which sounds like is exactly what you would like to
I want
to see.
Do that and verify it.
Yeah, and like there is that generally gets pushed back at TC39 because we're worried about websites optimizing for one specific version of one specific engine, and we think like that over time will just end up being bad for the web because people will start just, it's like the inline thing in C++. Let's just put that inline thing everywhere, and the compiler still does what it wants anyways, right? So we can end up in the same situation with JIT compiled code where people are trying to put it on everything because that's what's going to make it faster, even if it ends up trying to use a ton of memory or something like that. But yes, in terms of your more specific question, I'm not sure if there's a way of seeing that in our dev tools or not. But I kind of guess not, because we do typically try to hide it.
Yeah, probably not. But I'm now wondering if I can do it.
And there might be, if you're working with a V8, because they are proposing this compiler hint, it might exist in V8 already as like a non-standard thing. So, yes.
When it's jitting, so for example, like there's function A which calls function B, right, and function C is inline. And if it's in a hot path, will the native code basically the equivalent of C++ inline, right? Will it merge that, or will it be two separate?
Like inline a function?
Yeah.
Yes, I believe that would happen at the mirror level in Ion, where we had like that optimizing step. I'm sure. I mean, if I worked in that area, I'd be able to answer for sure, but I'm 99% certain we do that. Yeah. Yes.
I wanted to ask about dynamic mixed types in an array. Like how is that handled because you mentioned there's the happy path where there's inline cache because it gets typed in and stuff like that. But how does it handle an array with mixed type objects?
Okay, no, that's a very good question. So, yes, of course, which I should obviously repeat. So the question is, what happens if you're working with an array with mixed types in it? How does that affect inline caches? So what I talked about was the simpler example, which is what Smalltalk implemented in 1983. But that concept in the Self language in the 90s, they added the idea of a polymorphic inline cache, which means instead of the simple idea of we'll check one type and then fall back to the complicated handlers, what we can do is keep an array of different handlers. So we might have int, and then after that we can rapidly check if it's a string, after that rapidly check if it's something else, and then fall back to the general purpose handler. So it's not actually just a single value in an inline cache. We might have, and I can't remember the exact number, but maybe up to 10 things in that cache before it would fall back to the general case handler. Yes?
Maybe a question about the TC39. What is the top problem for TC39 right now? What is the biggest thing that you're working on?
I'm not sure I want to answer that on the record.
Oh, okay. Maybe later.
I can definitely answer from my point of view, which is I think the language is just becoming too complicated. And so people keep asking to kind of include their kind of little pet feature, which would make their life easier in one small area without considering the overall complexity of the language as a whole. And I think And the feedback we get is that we're engine developers, we're not web developers, we don't know what web developers want. But we do have to implement this thing, and we can see the complexity that just keeps growing and growing and growing. And like we have had a case where we hit a security bug that was caused by the actual specification specifying something that had a security hole in it. So like I think these are problems that we'll face more in the future if we continue to add complexity to the language. Yes?
Oh, that was nice.
Oh, you want to tell me I'm out of time? Okay.
Yeah.
Okay. Yeah. Thank you. Yeah, thank you, everyone.